Hello everyone, I'm Alex, and I'm happy to be presenting our current work at the Cross Symposium. So many thanks again for the invitation. I'm going to talk today about our current work on offloading computation from Apache Spark to storage systems. So what we want to focus here is basically storage systems that can run interesting kinds of computation, or in other words, computational storage. And this work is in collaboration with our friends from UC Santa Cruz. Okay, so let me actually begin by introducing myself and my background. I'm currently an assistant professor at Leiden University, which is, the oldest university in the Netherlands. Here, my main topics are related to improving large-scale systems with a special focus on performance evaluation. And I'm also interested quite a bit in clouds. And one of my favorite activities is improving the performance of large-scale distributed data processing systems. Next to my academic appointment, I'm also collaborating with the industry where I work as a visiting academic for Amazon. I'm embedded in the AWS Lambda team, the serverless division, where my focus is on improving the performance of Lambda. Now, overall, I have a quite broad background, having worked in the past with HPC applications, GPUs, distributed in-memory storage. And for example, I also built a indexing subsystem for Apache Spark. All right, so let me start by having a deep dive into the topic of today. So in clouds, compute and storage are typically decoupled. There are several companies that offer data processing in the cloud as a service. And one of them, DataBricks, from which you'll hear talk about today, has written a blog post about this kind of topic several years back. So they explain here why they chose to store data in Amazon S3 rather than on, for example, a self-managed HDFS cluster. And the top 5 reasons for that are cost, achieving proper elasticity, or in other terms, scaling compute and storage independently, having tighter SLAs as the ones offered by the cloud provider, getting transactional rights, and data integrity, and last but not least, achieving a better performance per dollar. Okay, so they did that. Also, another company that offers data processing services in the cloud has a similar approach. Snowflake, this is the second company, built a disaggregated storage layer based on Amazon S3 as well. And the reason that they listed in the paper presented as at NSDI 20 is similar. So what they wanted was to achieve elasticity through scaling compute and storage independently. Okay, so in the end, building data processing in the cloud looks similarly to the picture that I have here on this slide. We have a typical compute cluster formed of machines or virtual machines ready to process data. And these machines communicate through a network layer to some large-scale cloud-based storage layer. And this can be Amazon S3, Azure Storage, or Google Cloud Storage, or you name it. Now, all of this type of design works pretty well for achieving separate scaling of storage and compute. There's also one problem that we might need to solve going forward. And I'm going to talk about that problem on the next slide. But all in all, this kind of design is both a challenge and an opportunity. And I'll explain why. Okay, so already several years back, there's been several teams of researchers who identified that the CPU is the new bottleneck in data processing systems. Now, storage and networks have grown faster in the previous years, and they started to put significant pressure on the CPUs to process data that comes into the processing system very quickly nowadays. So what does this mean? Well, compute clusters are limited in scalability, they use too many resources, so the overall efficiency of the entire ecosystem may be lagging behind. So what can we do about that? Let's see. Because the key question here is the decades-old question, which is, can we move some of the computation closer to the data? People have tried in the past to optimize for data locality, because this would reduce network traffic and also alleviate some of the pressure in the compute cluster as well. Okay, so what enables us to do this with this kind of system design? Well, in modern storage systems, the machines that store the data are not simply dumb storage area and networks anymore. In the cloud, they usually are full-fledged machines which have CPUs of their own, which can actually help in processing of this data. And moreover, and perhaps more interestingly, nowadays we have storage devices which have specialized hardware, like small, tiny FPGAs, for example, on the storage device itself. So that tiny computational device can also perform some form of computation. Okay, so now, irrespective of how the computational capabilities are designed at the storage layer, we'd be very happy to actually tap into that and to use that to alleviate some of the pressure on the typical compute cluster. Okay, so in this project that I'm talking about today, in this line of work, we want to find a good model for shipping away some of this data processing computation. We assume that the compute cluster here is Apache Spark, because it's widely used nowadays, it's open source, there's a large community behind it that we can interact with. So that's perhaps what we can call the de facto standard in data processing. And we'd like it to, interact with any kind of distributed storage that has computational capability. Okay, so what do we need to do to achieve this computational offloading? In our opinion, the most important part is adhering by these 3 requirements we found. So first of all, we'd like this offloading to be pretty general. So we'd like to be able to offload to multiple types of computational storage, multiple types of data formats like Parquet, Arrow, ORC, etc. Yeah, so if we want Spark to offload computation, we shouldn't just have a one-off connection to some system that can do that. It would be a good idea to be able to connect it to multiple. Second of all, we also think that it's a very good idea to actually decouple the storage logic from the computation engine. So nowadays in Spark, for example, whenever we want to connect to a new data source, we need to write some form of a connector. So we have JDBC, ODBC connectors. There's a connector for MongoDB, for example. There's readers for many kind of file formats like Parquet, ORC, CSV, you name it. So in principle, we'd like to take all this functionality from the Spark code base and move it to a separate storage layer that encompasses everything, all of the things I just talked about and mentioned. And possibly also having the capability to put out some computation in case the storage can actually support that, and just have a layer that does that separate from Spark, and then Spark can just tap into it. So for all the new kind of connectors, formats, storage engines, we would just need to modify this thin layer and not add functionality to Spark. Okay, the third, and I think one of the most important requirements here is that we'd like this connector to be as fast and as efficient as possible. So it shouldn't introduce much or any kind of overhead, because then, you know, who would actually want to use something that's inefficient? Okay, so our solution. Given all that, all those requirements, solving the problem and matching them, we've come up with this connector, or a middleware layer, if you will, that connects Apache Spark with other kinds of storage. And in principle, we'd like it to be computational storage. So we've managed to build this as a lightweight library that can be added on top of Spark. So you would just need to include it in Spark programs. So you won't need to rebuild Spark or anything. And legacy Spark applications, Spark programs would just work. You would just need to change the data loading part, and that's it. Now, to achieve all that, we've made extensive use of the Arrow dataset API. Just a few words about that, because you're going to hear more about Apache Arrow, I think, on Wednesday, when the very authors will actually talk about it. So I won't talk too much about it, but what I will say is that the Arrow dataset API gives us functionality to work with tabular datasets. It understands many formats: Parquet, Feather, CSV, and there's a promise of many more to come in the future. And also it can already express some computation and move it toward the data sources. At the moment, we take advantage of filters and projections, but in the future, I guess we could probably express more generic types of computations, or even directly user-defined functions. So we could have for example, Spark users write the UDF, and we could simply ship it to computational storage. That's one of the things that we might do. Okay, so how does the connector look like actually? Well, we can actually represent it as in the diagram on this slide. It's important first to notice that Spark, so this part here, is a JVM-based system. So it's implemented in a JVM-based language, Scala, Java, and so on. On the right, the Arrow dataset API is implemented in native C++. And of course, between the two, there's this Java native interface that we've had to build. The figure is relatively complex and shows the entire data flow through the system. So we have, for example, a Spark worker, which makes a read request to this Arrow file format, which we've implemented. This one will, for example, scan something from the scanner, which you also implemented. Then this is passed through the JNI to the dataset implementation, which goes to a file format, which can be Parquet, CSV, ORC, IPC, or this newly added thing called Rados. Then everything goes back in this stack through all these complex arrows, giving data back to the Spark user, to this vector loader, and then the response is back here at the Spark worker. You've seen here this Rados file format and the Rados data source and the scan task. This is because the computational storage we are actually working with is based on Ceph, We're going to hear more about this on Wednesday, so I'm not going to go too much in detail here. But what's important to notice here is that we try to keep the data copies and transformations to a minimum. One of the copies would be here, and there's a transformation from column vectors in Arrow to columnar batches and rows in Spark, because Spark works with rows. Okay, so given all this complexity with all these arrows that are difficult to explain in just a few minutes, is this in any way efficient? I can show you here an experiment where we just scanned without any kind of computational storage. So we haven't offloaded any kind of computation. We are just simply reading Parquet data with data set sizes ranging from 70 something gigabytes up to 4.5 terabytes. And with these two colors, with light blue, we show Arrow Spark, which is basically Spark plus our connector. And this is with darker blue vanilla Spark, simply Spark, which reads this Parquet data through its own connector. On the left vertical axis, we have execution time. And on the right vertical axis, we have the relative speedup of Arrow Spark compared to vanilla Spark. For the smaller data sets, we see that there is a slight slowdown, but as the data sets increase in size, there is barely any difference between the two. There is even a case where our connector is actually faster than the default way of reading data for Spark. All in all, actually, what we can say, and which is really good, is that the connector is zero cost. So the performance it has is really on par with vanilla Spark. And that's actually super good news, because it means that the connector is giving you data as Spark, as vanilla Spark would actually give it to you. And if we would do some computation offloading, that would be even better, because this connector would not introduce any kind of overhead. So we can just tap into the advantage of just offloading computation, which is really cool. Okay, so how do we program it? I said it's really simple and we can take advantage of it. So initially, we would just need to import this Arrow extension we wrote. We build the session using that extension, which is just a few lines of code. Then we read the data using this Arrow reader that we implemented. I showed that to you in the slide with the diagram. And then everything just should work. Any kind of code that you could write, any kind of Spark SQL code or whatever will just work. With the added bonus that we can do push downs of filters and projections that could be actually executed in storage, which is a very nice feature. Okay, so one important question is, what kind of storage can we connect to actually? So in principle, the good part is that we could connect to any kind of storage that offers Arrow dataset bindings. In reality, because this is a new line of work, at the moment we have only this Skyhook data management project that does computational storage on top of Ceph. It's built by the team led by Carlos, and you're going to hear more about it on Wednesday. So I'm not going to spill the beans and say much. Okay, so how can all this thing actually help Spark clusters? So I have an experiment I can show you with all that. We have Spark here, we have the connector in between, and the storage cluster with Skyhook, storing a 10 terabyte Parquet data set, and we want to filter 1% of that data. In the case in which we wouldn't offload the filtering, what we do is that we read all the data through the network and do the filtering on Spark. And if we're lucky and we can offload the filter, we can do all the filtering in storage, and over the network only goes that 1% of the data, and then Spark can actually read it here and do whatever it wants to do with it after that. Okay, so given that experiment of a 10 terabyte Parquet data set with 1% selectivity, we measured the reduction in CPU utilization for the case without offloading versus with offload. So on the left side of the screen, we see the CPU utilization of the Spark cluster, which reads in the entire data set, then applies the filter. And on the right side, we see this compute CPU utilization for the Spark cluster, which pushed the filtering and gets back only the filter data. And the interesting thing, or the really good news here, is that we have a CPU reduction of about 4.5 times by looking at the areas under the two curves. Similarly now, if we are to actually look at the network traffic reduction, same experiment here without offloading, here with offloading. And we just measured the network I/O that the Spark nodes do. Here we see that we basically need to spend about 1.5 gigabytes of traffic per second quite frequently, whereas if we are able to actually push down the computation and get only filtered data back, we get about 50 times less data over the network, which is very important. And you know, if you are a cloud provider who has a lot of clients, it's perhaps a good idea to reduce this traffic to serve even more clients or give them good QoS. Okay, so now to conclude, computation offloading from Spark to our storage is actually possible, and we have a prototype doing that using only open source software. We also strive to open source the prototype that we have. We have promising results, which I just showed you. Of course, as with everything, there's improvements that could be done. So if I'm to just pick one, basically, as I said when I showed you the diagram, the arrow format is columnar, Spark operates on rows. So for example, it might be a good idea to make Spark operate directly on the arrow data, so we don't have that transformation anymore. Now, if you have any questions, I'd be happy to actually take them either live during the Cross Symposium, or otherwise you can just shoot me an email. The address is here. We can also communicate through LinkedIn or any kind of means of communication you'd like. And to actually end, again, really many thanks to all the people who actually contributed. Thank you very much.
Any questions for Alex?
Well, I put some in the document.
Okay. Yeah. Do you want to go ahead and just ask it live?
Yeah, sure. So you started off saying that CPUs are the bottleneck, and that's a pretty broad statement. And I'm not sure, why you start off with that assumption. Sure, lots of people say that, but is it really? Then later in the presentation, you talked about CPU utilization. Well, my follow-up question to that is, how do you compute CPU utilization? Because if it's what's reported by the OS, very often that's highly inaccurate. So, this idea of programmable storage always has bothered me, because you're shifting cycles from one place to another. Is the place you're shipping it to have sufficient cycles to do it, or not? And is the original premise valid? I mean, there's been a long history of the balance between distributed processing and mainframes, and what's your goal? Is it latency? Is it bandwidth? So I'm just challenging some of these fundamental assumptions, and it's not actually directed at you. It's that people just jump onto that bandwagon without, I think, without often thinking it through.
Yeah, thank you very much for the question and for the comment. So that's a very valid point. We've often thought about this and also I think struggled with these points ourselves. So for the first question, you're basically asking whether we know for sure that CPUs are a bottleneck with these kinds of systems. So to yeah, be more specific, I'm actually talking about systems like Spark that do distributed data processing, right? And there is already quite a bit of body of evidence showing that for multiple types of reasons, CPUs are the bottleneck in Spark. So one could be basically the implementation, which may not be super efficient because it's a JVM-based kind of implementation. And if we had a native implementation, then some of that added overhead would be smaller, so there would be less pressure on the CPU. That's one thing. The other line of reasoning there is that networks, especially networks, but also storage, have become so fast that pushing data to CPUs and processing that data at the, let's say, line rate is not doable anymore. So there's evidence for that, and there's a very cool paper about it that I cited in the presentation, and they basically show that, and they show that you would need, for example, some GPU or a couple of GPUs to actually process the data that comes at line speed or something like that. So that's one part of the question. And the second part of your question, so I'm actually reading from the Google Doc, is whether we know if there are sufficient excess cycles on the storage layer. So that's something very fundamental that I don't think anybody knows much about, except if you were a big cloud provider like, I don't know, Amazon or something, and you would know what happens behind S3 or something and how utilized those machines are. And I cannot give a definite answer there. The intuition is that there should be some spare cycles. And I think even if there aren't that many spare cycles, maybe doing something together between the computation engine and the storage engine could actually help alleviate some of the pressure on the computation engine, actually. So, working together rather than, just pushing everything there blindly and not caring about it, I think would be a good idea. So, whenever the computation part is too busy, we thought about this mechanism of pushing back some computation, saying, hey, don't do that anymore, back off and do your own stuff. I will just give you back all the data and I will not run any kind of computation on your behalf. I think you're muted.
Yeah, I would suggest that the idea of dynamic load balancing or adapting the schema could be very, very beneficial. I'll also say, and Carlos has heard me say that many, many, many times, dynamically adaptive systems can yield huge results. The other thing I would say is when you measure things, sometimes you get surprised. So I wrote a paper in 2018, which took the number of threads down by a factor of 10 and sped up the computation by a factor of 15 by doing that. That was not what I was expecting. So, you got to measure some of this stuff. That's my advice.
Yeah, thank you, Ike. Any other questions? I would love, this is a great discussion and we can spend more time on it, but I want to also make sure that everyone asks questions, wants to ask a question. Any more questions for Alex? So maybe as a follow-up, right? So one of the things that that also is interesting is how CPUs are packaged with memory bandwidth. Often, you know, you have to get the memory bandwidth for doing medium bandwidth and bandwidth intensive tasks, which happens often with I/O. You will have to buy a lot more CPU to get that memory bandwidth, right? And so there was a really nice talk, I think it was last week or the week before last week in SDC, a Storage Developer Conference that's organized by SNIA, by Brad Settlemeyer from Los Alamos National Labs, where they found out that writing files to storage through it's just a normal file system, right? They ran out of CPU, but when they actually dug deeper, it was actually not the CPU they're running out of. It was just that the smaller CPUs that they really wanted to use because they were otherwise it was too costly, didn't have enough memory bandwidth. And so they actually added processors on their storage layer to alleviate that. And so, because that processing power, that was like specialized processing power that was, you know, that was embedded. And in fact, when they say storage layer, it's actually the local storage layer. It's the storage layer that's on a device level of direct attached storage devices, right? And they can do all kinds of things by just attaching additional processors to the PCIe bus. And then group that, you know, they own a certain number of storage devices, right? And so by essentially outsourcing some of the processing in their IO stack to those processors, they could use much cheaper CPU because they didn't need the CPU bandwidth. And so that was an interesting effect that, so yeah, I totally agree that when we say higher CPU utilization, it is not exactly the cycles that we might be talking about. It might be just a packaging problem, but it is part of that what we are trying to explore in computational storage and what other people do in computational storage and in programmable storage is that it is essentially a recomposing of the IO stack.
Yeah, but it's not the IO stack. It's processors and memory. It's not necessarily about storage. That's what I'm saying.
Yeah, but I mean, we're storage people, and so we're trying to do our part of in that game of rebalancing things. But really good point. Other questions, comments? Yeah, I think, Alex, do you want to answer Ike's second question, how we measured CPU utilization?
Yeah. So I think that's also a really, really good point, and which basically ties a bit into what you said earlier. So yeah, basically CPU utilization as reported by the operating system is just some magical number that doesn't necessarily say much. And at least for the results I showed here, we basically took the bait and we're reporting those numbers. So we're just reporting what a open source tool actually gets from ProcPid, which is not much. But of course, it will be a much better idea to dig a bit deeper and run tools like perf or something and see where the cycles are actually spent, and maybe, you know, try to understand whether really cycles are a problem or the memory bandwidth is a problem, or, you know, what's going on in there. So we haven't done that, but it should be really high on our priority list.
Thank you.
All right. If there are no more questions, I'm going to try and not do a better job with John's talk. I think I learned a little bit about how Zoom shares audio with applications. So let me try this again, and hopefully it works this time. So let me see.
Thank you very much.
Thank you, Alex.
Hi. My name is John ODwyer, and I'm here today to discuss the Delta Lake architecture with you. Before getting going, just wanted to give a little background on myself. I'm a developer advocate here at DataBricks. Before joining the developer relations team, I was a solutions architect at DataBricks for 4 years, and before that, my whole career I was a data scientist and also a software developer. Outside of work, my family and I we live in Denver, and we just love being in the mountains, either running, biking, or skiing together. To start off, I want to discuss the Delta log. It's actually the transaction log that is at the basis of what Delta Lake is. The transaction log is a set of table versions that are associated to the Delta table, and also an optional partition that is associated to one or many columns that are associated to that table. It's also then underneath that is where the data actually lives, which is the data lives in a Parquet file, or sets of files, excuse me. This is the basis. All of this lives on object storage, whether that be AWS S3, or in the case of Azure Data Lake, and the like. That object storage is the basis for all Delta tables. It's also where all of this data lives. And really at the core of all of this is Parquet and transactions that are the metadata that are held in the table versions in JSON. So I did mention versions a couple times already. What is a version? It's essentially the last version plus some actions, and what are those actions, and what make up those version sets? Well, it would be whatever was in the last set plus the change that's associated, hence the name Delta, the change between the last version and where you are now. Those are metadata that's associated to that changed value set. Generally, that metadata would be around the schema itself. There are other pieces that can be changed as well, such as names and partitioning. But generally speaking, the metadata that would be changed would be a schema, and in the case of schema evolution. Other values that are kept in there and the actions that happen is when a file is added or removed. We'll get into what that looks like in a second as well. The result is essentially, the metadata, the change in metadata plus the lists of files that are associated with the current version of the table. Delta is an atomic table. That is great for anyone that's pumping data in and also reading the data that's associated at any time. What I mean by that is as versions happen, when you read, if you are reading it as a batch file or batch table as opposed to a streaming, it would actually read the last value, the last case of a table, version of a table that existed. Let's say it's version 1 that you when you say select star from, you would get version 1. If values were added since then, all of those are also ACID transactions. So at a row by row level, they are added as needed. And when you came back and you did the exact same SQL command, it would actually get those next versions, which may be version 2. So how does this work? And is it possible to have multiple writes at the same time? It is. The way that conflicts are taken care of is that they're taken care of optimistically. What I mean by that is whoever gets there first writes first, and then whoever doesn't has to understand the changes since the last time they tried and then retry after the fact. Generally speaking, what that looks like is two people would read the same value sets. User one would write their append in, and at the same time, if that conflicted with user two, user one got in, but user two did not. What then would happen would be user two would check for anything that actually was different from where they were initially. They would then reassess and try again and write in. So one thing that actually comes into play is that this is a lot of data, and it is big data. And not only is the data itself big, but the metadata is also big. And how do you handle such large amounts of information? Well, we use Spark to do that underneath everything, specifically using checkpoints and Parquet under the hood, and that's really important. And the integration between Spark and Delta Lake is very important as well. Although there are other ways to read Delta tables, but at like the underpinnings, there is a very close relationship between Spark and Delta. That brings up a point of how do these two technologies relate to each other? I believe that a lot of you use Delta now, or sorry, use Spark now, and you can think of Delta as a different format that you would read and write to. It has just like you would for Parquet. It has a lot of extra features that we will get into that allow for various architectures or manipulations of data that weren't possible before. But at the core, you would interact with Delta in the same manner that you would interact with Parquet or CSV or JSON files, which is reading massive amounts of them in Spark and putting them either into a data frame or writing from a data frame into the format. This is, as you can see, really what you're doing is you're changing from format Parquet to format Delta and really reading it into a data frame and manipulating those files and data in the same way that you would before. I know that a lot of people in the audience are also using Apache Arrow. It's an incredible technology. We use it internally to Spark as well. And I did want to just briefly touch upon what the relationship is between Arrow and Spark. Currently, there isn't actually a direct relationship between Arrow and Delta Lake, but there is one between Arrow and Spark, and it is used. Spark or Arrow is used for the in-memory transfers of data between JVM and Python. Specifically, what it's actually used for right now, well, actually generally, the use case that we see for a lot of these transformations is when you're doing single machine Python ML. And what you need to do is move massive amounts of data from the drivers to the workers, and moving that efficiently using Arrow is incredible. This is something that I see on a daily basis. When I was a solutions architect, it was actually something that I would show people continually, because it's a pretty transformative experience, especially in the relationship to how long it can take to actually move some of this information and how much faster it can be done using Arrow. That's the current. That's currently how we use Arrow in Spark. It does need to be turned on in many cases, or using specific features such as Pandas UDFs, which actually employ Arrow. And I do want to point out that not all data types between Spark and Pandas are directly relatable using Arrow. It is in the documentation, which I have here, which you can actually explore after the fact. These slides will be available. What a lot of the features that we'll discuss here today, and also many features of Spark, allow for something that we call the incremental ETL architecture. In the case of what we're talking about today, the Delta architecture, a lot of the pieces that allow for this is the incremental nature of changes in Delta, and also Delta, the fact that you can actually do row-based changes, the incremental nature of those changes, and then also the ability to use Delta as a source and a sink of streaming data allows you to really build out an architecture that you can have multiple stages of tables throughout an ETL process. And also then manipulate those and change only the pieces that need, or rows that need to be changed. What I mean by that is, let's take, for example, an ML model, which usually has a heavy amount of featurization to get to the feature tables that are needed to actually do that modeling. Well, what happens if something upstream from there had to change? Let's say something had to be recalibrated and a new value had to be taken into account, but only one row of that value changed. Instead of having to, like the old days, delete all files where that row, delete the file, but also identify either which files that row is in, or blow away the full data set. You can actually now go upstream, change only the row that needs to change. That change would be identified in that Delta table, then can be progressed to the next table where only that one row could be changed or deleted, and downstream until you actually get to the full featurization set that's needed for ML. This is a very impactful thing for all of our customers, especially ones using advanced analytics. Two major features of Delta that are directly related to schema are schema enforcement and evolution. We'll start with evolution because Parquet, which is at the core of Delta, allows for schema evolution. The real problem here, though, is that evolution can evolve into a place where it's incompatible with other files that are other Parquet files that are associated at in the same table. That can break your table, and that's something that we had seen in the past with with a lot of different object storage big data solutions, and so we solved in Delta. What Delta does, as you can see, it has the transaction logs at the top. Those transaction logs are essentially the guardrails for those schemas, so that it can evolve. Those schemas can evolve without breaking, without evolving in a way that would break. The schemas are also enforced in Delta tables. By default, they are enforced and will not evolve. To allow that evolution to happen, you explicitly have to change the configuration on the table so that you can allow that evolution to happen, and it will evolve. It will either throw an exception if you did not allow for the table to evolve, or if you're trying to evolve a table in a way that is incompatible. For example, if you tried to change a string to a decimal, and there were strings that are not decimals in that column, then it would throw an error. Next thing that these different versions allow us to do is to do something pretty cool called time travel. Time travel is essentially pinning to a version of a table from the past. So when you just say select star from my table, that would get the current version, but you can say either select star from my table as of version or at version. You can do the same in Python. This is also possible with a timestamp as well, and you can give a timestamp or a date and do the exact same thing in both SQL and also in Python. A couple limitations of these is that the main things that I wanted to point out was that both the transaction log and also the data that is associated to that version need to be there for that time travel version to be recognized and read. For that reason, it's not a very good idea to use time travel for months or years at a time, mainly because of the vast amount of storage that you would actually need to keep around, and also the state that's associated in the computation of doing so. So the other thing that this time travel and also versioning allows for in Delta tables is shallow and deep clones. What these are basically two different ways to say, I want to attribute a point in time of a Delta table. The shallow version of these tables are, or shallow version of these clones, excuse me, are essentially just making a clone that says, I want to point at this version of this table, and that's it. It literally just will point to the version that existed at that time. A deep clone will copy everything that's associated, including the data of that version, so you can clone everything as is, and it can be completely self-sufficient. A shallow clone cannot be self-sufficient and adhere to the same rules as versioning. These are actually great for both backups and also for ML. In the case of ML, it's a great way to have reproducible models. Couple other pieces, but because of time, I wanted to just point these out. Is you can update a row on row basis in a Delta table. This is something that's really not possible or at least was not possible before in object storage. This allows you to not only have to blow away a full table or a file, but you can now only change the value at that level. You can do the same thing for deletes, where you can only delete values that are associated at a row by row value. We also have something called an upsert. This might be new for people, but an upsert is essentially or a merge statement is a statement that allows you to do all of these different conditions in one place. You can do inserts, updates, and deletes all in a merge statement together. A couple pieces on performance that I did want to point out is partition pruning. Partition pruning is something that is available in Spark now, but you can also take advantage of it in Delta, where on a partition basis, say for where statements that are associated, it will actually take those into account and not look at any of the data that's outside of those sets. Another type of data skipping that is available in Delta is actually on a row basis, or on a column basis for a file. It will actually track statistics that are associated to those files, such as min-max values on the columns, where so that you don't actually have to interrogate all files for a where clause. It will go through and it will actually identify what files you actually need to look at to take care of to find particular pieces of data, and it'll avoid scanning irrelevant file sets. I had mentioned before that streaming was available in Delta as well. This is, making a table a very easy source of a stream is pretty transformative. What that allows you to do in the case of Delta is, and since Delta is not only you can also update rows, you can have a streaming table that joins to a batch table. And this is actually a very cool thing, where that streaming table will continually stream. But if that batch table changes in a way, let's say it's a slowly changing dimension, those joins will actually identify the change in the table, and that new joined table, the streams off of that new joined table will actually adhere to the changes that happened in that joined batch table. It's actually a pretty transformative idea, something that I actually wrote about a while ago. And thank you for taking the time today to listen to me talk about Delta and the Delta architecture. I'm really excited to start the conversation, and if you have any questions, please let me know. Thank you.
Thank you, John. There he is in real life. So any questions? We have a couple of questions in the Q&A document. I don't know whether you had a chance to look over them. One question is from me. It's more like a simple clarification question, right? When you talk about formats, Parquet format versus Delta format, you don't actually mean the format of the files that are being stored. You mean just how you interact with them. Is that correct?
Well, it's a little bit more complex than that. Essentially, Delta is putting in a transaction layer over Parquet, right, essentially. So it's not really, when you talk about the Parquet format, you're interacting directly with the Parquet file format in Spark. When you talk about interacting with the Delta format, you're actually interacting with the transaction layer that then in turn interacts with the Parquet files at that lower level. The reason for that is really there's no way at a row basis to update a file in Parquet in big data. Really what you're doing is getting like you're replacing that version with the next version that was created from it. So I guess it's more that it's not necessarily Delta is a way to manage those Parquet files and the versioning that's associated to it, but it's not necessarily like it's that you're interacting with that higher level as opposed to the Parquet itself. I don't know if I answered your question, Carlos.
No,
apologies. Does that make sense?
No, it makes totally sense. I think that it's just an unfortunate overloading of the term format, right? And we actually ran into exactly the same issue, because when we actually created a new backend for Arrow, right, for using Ceph storage to offload some of the Arrow operations, the first suggestion was made to us is that, yeah, just create a new format, right? So instead of going to like Arrow Parquet format, we just did Arrow Skyhook format, right? And which is not the same, because we're still dealing with Arrow data, right? And we don't introduce a new format, but it's essentially, format is sort of suddenly a new word for backend. And that's the same thing here, right? You're just creating a new backend and how you treat the data, and you operate on that data in a new backend.
Yeah, and really when we say format, it's essentially like if you look at how you access, and I can bring this up if you like. When you discuss the format at its core level, it's really two things. It's actually the format and where, and to your point, like it's really where in object storage you're actually accessing it and what you expect to look at. Because really when it comes down to it, this same path can have Parquet under the hood, and it does in the case of Delta, but you're not actually necessarily looking at the Parquet, right, because there could be duplicative sets that are associated to it. So.
Yeah, and I fully understand, because it's really a nice way of abstracting things without having to change your programs, right? Because all your other stuff still works, and it's just that's how you open the data set. So
yeah.
All right, yeah, that was just my. So Alex, do you want to ask your question?
Sure. So first, thanks for the presentation. Really cool. Now you talked a bit about how Arrow is basically used within Spark, and I was wondering whether you had any plans, or whether even if it's a good idea to just make Spark compute directly on the columnar Arrow representation rather than the kind of row-based format that Spark operates on now, so the unsafe row thing.
I would definitely be talking out of turn if I said that there were plans for it or to speculate on that. But from my experience, and it's definitely an experience of like implementation with customers, and also my own implementation of my projects internally, the Arrow, the way that we efficiently at least go from in the way that we currently use Arrow internally, like, well, okay, the publicly exposed way that we currently use Arrow, I'll keep it at that, because I don't think that there's other internal uses yet, but this is definitely the one that is basically from JVM to Pi, essentially, and that is extremely effective, and I've seen that be extremely effective to in certain egregious cases 10x that's essentially like when we were actually moving the data, it's so efficient that like based off of my experience, I think that we should employ that as much as possible. Now, I will, like, I do know that that's a naive statement on my part, because I don't know some of the underpinnings of what need to go into using Arrow more so. I think that at least for the, all the underpinnings of when we identify and when we go between a JVM to Python, it definitely, I think that we should probably be using it as extensively as we possibly can. With other interactions, I don't know the intricacies, but I do think that it's a promising technology that we should probably be employing as much as we possibly can. So to the extent that, like to your point, Carlos, about using it as its own format, if there was a way to do it, I would actually, and I think to your great presentation, Alex, it could be like how you access and use that API, but the underpinnings really for that format is writing and reading to object storage, which in the case of Arrow, it's in memory. So you need that extra layer somewhere. So I don't know how to go about it, quite frankly, but I do think that we should be using it as much as we possibly can. So, and happy to discuss that further if you do have suggestions or are looking for ways to actually do it. I can, we can talk through that a little bit further too.
Yeah, thank you for that. So the reason I'm asking is pretty straightforward. So in the project I was talking about a bit earlier, we're basically getting column batches from the computational storage in the form and shape of this Arrow in-memory representation. And then to make Spark do some computation on the reply we get, we need to do this transformation from Arrow to unsafe rows. And that, of course, takes cycles, takes memory bandwidth, takes whatever you want. And it's pretty inefficient, I think. So we were thinking of a way to just not do that, but perhaps make Spark understand directly the Arrow format and run directly on those columns. I know there will be a lot of stuff to implement, like to get it going, but maybe you get some pointers or someone to talk to about that, or maybe we get told, hey, it's not a good idea to do that, don't do it, and that would also be some good feedback.
Yeah, I think like if we go back into what you were doing, right, and that graph that you had where you're essentially showing that, and if I had it correctly, when you get to those extremely large data sets, that's where you really get the benefits of Arrow, right? And the key is probably the heuristics that are associated to where identifying the size of data that you're potentially going to be accessing, and then using it where possible. That's probably the first place that, but at the same time, that takes heuristics and basically you're building in breakpoints. What we're currently doing, you know what I mean? So that's essentially like there are points of, at least with the current architecture, that allows you to find where that is. What we're currently doing with the implementation of Pandas UDFs is essentially offloading that to the consumer, where they are determining if it's a good enough place to do that, essentially. And I don't know where those would lie. Happy to actually try to figure out the right people for you to talk to about this, so that the interactions would be better, and the architecture may lend itself in the right direction to going there, or at least determining if it's right. So we can definitely take that offline, and Carlos has all my information as well, so we could actually talk through that. But I can't speculate, unfortunately. Sorry to say.
Awesome. Thank you very much.
Yeah.
Thank you, John. So we're gonna get now to the sort of more informal part of the discussion. Unfortunately, we had the third speaker didn't come through, and so we have a little bit more time to discuss, you know, sort of the context of why we actually wondering about these things that we're discussing in this session. So one of the things that that happened, you know, in the last few years, I got involved with the high energy physics people, and they're having a really interesting problem, right? They have the LHC, which is like the data source. I mean, there's a bunch of other accelerators in the world, but LHC is the biggest one by far, and they are getting to the point where they cannot put more energy into the LHC, but they can bundle the energy tighter because of advances in magnetic technologies, right? So they have like this big ring and everything is in magnet fields, and they can bundle it. So they say that they call this higher luminosity, or HL. So there's actually a new version of the LHC coming online in a few years. It's called LHC HL. High luminosity, and so it's essentially the equivalent of having more energy in the ring, and you can sort of go beyond what they, you know, next higher energy levels, and they have good indications that higher energy levels will lead to new physics, and the why. So then, you know, this community is really well organized, and they realize pretty quickly, well, the amount of data that they have to deal with is much higher, and they don't really have the technologies given their current bottlenecks, and they don't have the technologies to actually really deal with that. So they founded this institute. It's an NSF-funded institute for innovation and research in software. Or IRIS, and there's like an IRIS HEP, there's also other irises, right? But there's basically, these are the institutes that are looking at kind of the ecosystems that the science community need to have in order to be successful. And that's going to be both in-house tools, right? The high energy physics community has a lot of tools. They have their own format. They have, over the decades they worked together, figured out that they really need a two-dimensional table. But this two-dimensional table has certain properties that makes it really hard for traditional databases to deal with it, right? So there's, they called it actually, they have a Python package called awkward array, because there's a lot of embedded stuff in these tables, and they're kind of awkward. And so it turns out I got involved because that community also happens to be really heavy Ceph users. So they love Ceph. They use Ceph extensively in their community. It's a storage system that works really well for them. And I was interested in saying, well, you know, you have these data management problems, and over the last at least 10 years, I've been trying to get more data management functionality into the storage layer. And so we've been working in Cruz, you know, since 2016. I think we started this incubator, the oldest incubator project, which is Skyhook, which is basically using some of the research we did in programmable storage systems and actually applying it to table data. And we had sort of our in-house attempts, and after a few false starts, we discovered that Arrow is actually, you know, the ecosystem on Arrow has actually pretty much everything we needed. The computational models, the really efficient way of representing things in memory, the no copy or zero copy frameworks. So we actually switched over to, plus the high energy physics community also really wanted us to to come up with interfaces that they can use, right? Really practical. And so it solved a number of problems where we could say, okay, let's use the Arrow dataset interface to to give them an interface. This is how it's going to look like, right? And then we've figured out ways to dump your data into the storage system, and then be able to actually offload querying to that storage system using embedded Arrow in the storage layer. And and it was only then that we realized, oh wow, since we are now in the Arrow ecosystem, there are like all these other things that now kind of fit to it. And in particular, they were actually building already data management layers that look a lot like Delta Lake or Apache Iceberg or other ones, except that they are, they're like in a much earlier development phase, and so so there's now this, and this is sort of actually the common theme of this institute, that they found that by adapting essentially their internal tools to the Python ecosystem, the scientific Python ecosystem, to like all these big data management frameworks, they found amazing ways to leverage these systems, right? And so it's not always straightforward because the data model is somewhat different. So this is actually where we are at this point, right? We have Skyhook that works with Arrow. We actually are almost have actually the Ceph plugin that turns Ceph into an Arrow native storage system is almost merged with the Arrow community. That the pull request is very close to that, and we got a ton of feedback, and it made the plugin much more elegant. But it also brought the Arrow community to really think about storage plugins for other storage systems and how they should accommodate those. But now Delta Lake is sort of on the other side, right? So when you have a infrastructure which puts a data management layer, transaction layer on top of all this data over the data lake, and you start to have backends that actually allow you to offload some of these operations, how would that look like? What would be the benefits, right? And this is the kind of things that I would love to discuss with you. We have already shown, Alex has shown that, that there are some really good benefits of offloading just CPU and bandwidth to the storage layer. But there might be others, right? So I can go on, but I see that John has likes to say something. I think you're on mute.
Yeah, I have one or two comments. One is that, yeah, the type of data management that you're talking about, offloading the storage, it's directly, that is what we're doing in the case of schema investment and schema evolution. There's actually a comment before about allowing, I think it was in reference, and maybe my ears were listening to it differently, about essentially allowing those schemas to evolve over time during the first part of the Q&A. That is what we're doing. It is what, obviously I don't know Iceberg as well, but I believe that they probably have some level of that as well. And that's exactly what we're doing, is basically offloading that type of enforcement to the storage layer. So, when you take that into account, yes, there is there's a direct correlation, and probably, aligning to these major open source projects is probably a very good thing. I will say, like, between there's this pesky thing called Spark that it probably enables, and also in certain cases may get in the way if you actually want to go directly from Arrow to like a layer like Delta. In which cases there's actually standalone readers and writers that are being developed as well. So those would potentially take away the need for Spark in the middle of that. If, let's say, I mean, for distributed systems, I'm biased, of course, but I think that Spark is an incredible tool for to essentially distribute things and parallelize massive amounts of in-memory data. Now, if you don't need that much massive in memory, and you can actually survive on one to a couple images, then potentially using readers and writers directly, or other cases where you want to use readers and writers directly in the case of going from Arrow directly to Delta, that it is a potential way to go as well. So keep that in mind.
Thank you. Yeah, so I think that the other sort of background is, so I talked a lot about this, the relationship to the high energy physics community, right? But there's also this, we have, through our cross members, we're very interested in the developments of computational storage, which is this idea of embedding computation in storage devices. And there's a lot of overlap, right? And it's also, I think it's more like a packaging problem, where SmartNICs, when you attach, a storage device, like a flash device to a SmartNIC, you can also call that a computational storage device, or you can create, have a fancy network interface to a traditional storage device that is also maybe a computational storage device. And there we saw other ones too. I mentioned earlier, what they do at Los Alamos National Labs, where they just have sort of a computational, basically data accelerators attached to a PCIe bus, right? That basically accelerates writing data to a file system. So all these things it point to like an IO stack that or kind of demand from an IO stack that you can more flexibly move different functionalities into different layers. And so the one thing that I think somebody told me that you really want the biggest expense in a data center is moving data, and you move data because mostly you move data because you don't have the context to compute the data where the data currently is. So you have to move the data to a place where there is the context, so you can compute what you want out of that data. And actually that you could, if you had a different kind of framework than you have today, you can basically prevent a lot of the movement of the data by more flexibly establishing context where you compute what you want out of that data, where the data currently is. So it's basically from our old traditions of like, there's a file system and everything below the file system is basically, you can't access it. There's nothing you can put in there. So we're looking for sort of blueprints that that allows us to embed things into the different layers, and these different layers can be on embedded systems like SmartNICs or even computational storage devices, right? So that is sort of like, I think our goal is to create something that can be very flexibly assigned to these different packages of how things happen to be put together, or if it's like a software-defined system in a cloud, right? That it gets assembled from the different parts, so that you can basically do this for whatever workloads or whatever needs. So I think that, and so we're in this in the research programs we have here at UC Santa Cruz, we're looking at, what do these new IO stacks actually look like? And I think Ike sort of brought up earlier, right? That you want to ideally be very flexible on how you assign physical resources to these different tasks in a stack, not only an IO stack, but any stack. And that's, I think, also part of our goal, is to sort of say, okay, if it's of great advantage to filter data, in a storage system, you can embed these filtering frameworks in that storage system, right? And do so in a way that doesn't force you to reprogram or recode or redevelop everything again, but to actually just take existing frameworks and just put them in there. And so that's what, in the Skyhawk architecture, which we will hear more about on Wednesday, we worked very hard to actually be able to do that. That even with a very fast, forward-moving community like Arrow, right? I think they come up with a major version increment every 2 months. We can actually keep up with that, right? So all we have, because it's just embedded, it's like nothing else. There's no extra code necessary, right? And how do you do that? And how does a storage system look like where you can simply embed these things? And where does it end, right? Is it the Arrow interface, or can we embed maybe even something like Data Lake into a storage layer, right? Where can you say, okay, enough of offloading, or sometimes, are we offloading too much, right? And how dynamic do we have to be? So these are all like the kind of research questions that we're trying to pursue here at UC Santa Cruz and in the University of Leiden. And to go back to maybe the question that Alex had to you, John, we would love to work with you on those questions, right? We see Delta Lake as an open source project, and we would love to contribute to it.
Yeah, and we're actually looking for help in ways to actually have contributors from the external communities, and it's a huge initiative of ours. Actually, it's probably one of the main ones in the company, and something that we would love. And it doesn't necessarily, it's heavily involved. Like I mentioned, it's heavily involved between Delta is heavily integrated with Spark, but that's by no means the only way. We're actually trying to find ways to divest it as well, so that it's not necessarily just a format that's used by Spark, but it's a format that is readable and writable pretty much anywhere. So that we can actually remove it from, and that's an ongoing process. It's actually being done currently in various ways as well. So those are other ways to do it. I don't want to consume all the time. Alex, do you have any comments or points that you'd like to make? I have one or two around how to extract values out of storage correctly, or not correctly, but without looking at everything. But I don't want to take up all the time.
Yeah, thank you. So I had a couple of questions that you basically answered before. So I was wondering whether, Spark is the only way to interact with Delta or not, but you answered that. Um, and I think that that was pretty important in the use case that Carlos presented at the beginning with Iris Hep, because I guess these people have a lot of other kind of tools outside Spark to interact with the storage. So that was one of my overarching questions. And another thing that ties a bit into what Carlos said before, Delta is an open source project, and we were kind of already looking into trying to offload computation from Delta towards Skyhook. So that's basically one of our second goals after we've managed to offload computation from Spark. And we managed to do some of that, but it's still an ongoing process. And I think that that's going to be a pretty interesting and neat thing to actually do in the future. So we'd be happy to collaborate and exchange ideas and reason about our designs on that.
So one thing along those lines, it's definitely not the only way to, Spark isn't the only way to interact with Delta. It obviously, because it was developed by us who developed Spark, it's going to be very integrated and well tuned. But at the same time, there's a lot of initiatives. Specifically, one that I actually put in the there's a GitHub repo that I would suggest that you look at that I put into the chat. It's the Rust. It's a standalone Rust reader and writer. And this is something that's being done by our community, specifically started by our friends at Scribd, I believe. And this is an open source reader and writer standalone that allows for interactions with Python and Ruby. And in your case, Python, I would imagine, would be the one that you would want to use. So that's something to look at and also interact with, because it will take, there are other, we understand that Spark isn't the only way to do this work, and that other people want access patterns for reading, and also then a lot of cases in what you're talking about, access patterns to write, so that, and to Carlos's point before with essentially the large bottleneck being around like the movement of data. I would agree. There's also, also to your point earlier, Alex, about CPU usage, that's definitely, from an economic standpoint, that's a huge cost and also a bottleneck. But around the idea of like computational storage and the access to storage with computation, or like that's associated to computation. One, there's two things. One, Delta with the pieces like with data skipping and partitions, that's kind of like metadata that's associated to essentially interpreting what you need to actually move as opposed to moving everything. That's one thing to keep in mind. Like those would be ways, and and there's no reason to reinvent the wheel in the case of Delta, but those would be ways that you can actually at least offload, the ability to only read what you need to. And that's essentially how we're doing it in Delta. And, that is an integration between Delta and Spark. That's one way to do it, is to actually do, when we do it, we're actually doing it when we're doing something called compaction, or you actually do writing. And that's where those reads can actually only be, you don't have to look at everything, so you only have to look at what you need. Another way that we're doing it, this is proprietary, but it would be like along the lines of your idea of computational storage is when caching locally to machines. And the reason I bring it up is, storage is 2 layers. We've been talking about essentially the object storage layer in the cloud for the most part, which is a big data storage layer. But there's also local storage on machines that came up. And that's actually one way that we're doing it is, I guess it would be a form of computational storage is around caching and what we call DBIO or DataBricks IO cache. It's associated so that you're like, and the way that we use it is purely around Spark, but it, we brand it with the Delta name. But it's Spark, it's Parquet and Delta tables that will be cached locally on the drives, and that computational storage stays on the drives and then will be interactively changed out. The reason why we do it that way is so that if it's in memory, you're either using what's ever in memory in the case of Arrow, of course, or you're essentially compensating for that by either writing back to object storage for spill or local storage for spill. So that's how we actually take advantage of it. And that would, I guess you could call that a computational storage with probably a liberal use of that wording, but that's also something that to keep in mind as well.
Thank you, John. And thank you, Alex. We have to unfortunately stop here. We're already 6 minutes late for the next session that has been already started. Great discussion. Thank you so much. And I hope you will be able to hang around more and join us in the next sessions as well. Thank you so much. And I see you in the plenary session again. All right.
Bye-bye.
Bye-bye.
Bye.